And last, but certainly not least, we need to talk about interference, which with sound is called beats. Now, once again, this is a concept that all waves do. We're going to talk about interference with light as well, but sound, really interesting things with interference. So what is interference? Well, interference happens when two waves, has to be two waves, when two waves interact, right? We've been talking about one wave for a while, characteristics of a single wave. Well, obviously in the real world, there's sounds all over the place, and those waves meet each other and they interact. All kinds of waves meet each other and interact, and it's called interference. Water waves meet each other and interact. They interfere with each other. Light waves interfere with each other. Rope waves can interfere with each other. Lots of different kinds of waves can interfere with each other, right? So interference is the basic thing that happens when two waves interact and form a resulting wave of higher or lower amplitude than either of the original two. And there's two basic kinds of interference that we're going to talk about. The first one is called constructive interference. That happens when two waves meet, and you need to write this word down, when two waves meet in phase, and that means when the crest of one wave meets a crest of another wave, or whatever part of the wave we're talking about. If it's a transverse wave, two crests meet, or two troughs meet together at the same place. If we're talking about a sound wave, we're not talking about crests and troughs, we're talking about compressions and rarefactions. So in that case, it would be with sound when two compressions meet up at the same place at the same time. The result of that is a single wave that is, just for a moment, higher in amplitude than either of the original two. So constructive, you can think about building, so that wave builds up. It results in a higher amplitude wave than either of the original two. And remember, amplitude in sound contributes to or determines the loudness, right? So we get a higher amplitude wave than either of the original two. In pictures, it looks like this. So this is not sound, this is a string, but imagine that two people hold a string on either end, and I'll show you a video of this in a second. They both create a wave that is a crest. So we got two crests that are meeting each other. These waves are meeting in phase, same parts of the wave meeting each other. Those crests add to each other, and in the middle, just for a second when they meet, we get constructive interference. We get a higher wave than normal, but it doesn't continue because those waves actually will just simply continue to move past each other. And so this wave was the one that started on the right. This wave was the one that started on the left. So the interference happens just for a moment when they interfere. Once that interference is done, they continue past each other. Let me show you a video of this occurring. So there are two people holding this little slinky, one on the right, one on the left. And what's going to happen is they're both going to create crests. The crests will meet each other in the middle. And notice we get a wave of higher amplitude than either of the original two. I'll run this back. The original two, the amplitude was about at this first tape mark. So we get amplitude about the second tape mark, I guess. But look at where it went to. It went up here. So we have a higher amplitude than either of the original two. But then those waves continue past each other. And I know they didn't bounce off each other because check it out. Notice that the one on the right starts out a little bit lower than the one on the left. Well, now look at it. Now we have a higher amplitude that's on the right and a lower amplitude that's on the left. That's a clear indication that they didn't, quote unquote, bounce off each other. They just simply continued past each other. And that's a great example of constructive interference. Now, the other kind of interference that we need to talk about is destructive interference, and this is opposite. This occurs when waves meet out of phase with each other. So instead of two crests or two troughs meeting each other, this happens when the opposite sides or opposite phases of the wave meet each other. If it's a string, which again is a transverse wave, it's not a compression wave, but it would happen if a crest meets a trough. With sound, it would be the equivalent of a compression wave, the compression part of the wave meeting up with the rarefaction part of the wave. If that happens, the resulting wave is lower in amplitude than either of the original two. So the waves meet up in the middle, they interfere with each other, and what we actually get is destructive interference. Now, in this case, there's zero wave in the middle. There's no wave whatsoever. They actually kind of cancel each other out. And the reason they cancel each other out is because they both have the exact same amplitude. the higher one is pulling up, the lower one is pulling down, and they just pull the thing down to the middle and there's nothing. That doesn't always have to happen, but what will happen is that there will be a lower amplitude than either of the original two, and that would happen if one wave is bigger or slightly bigger than the other. But interestingly enough, after the interference occurs, they once again continue to move past each other. They just pass each other like on a road. So the one that was a trough was on the right, now it's on the left. The crest was on the left, and now it's on the right. Let's look at a video of that one. Once again, gentleman on the right is going to make let's start this over. Gentleman on the right is going to make a crest, and the one on the left starts with a trough. The waves will meet each other in the middle, and just for an instant, we get nothing, right? It's hard to stop it right at that moment. There's no wave in the middle. You almost cannot detect the crest or the trough, but notice the crest started on the right. It's going to pass to the left, vice versa with the trough. And there we go. Here's our crest, and there's our trough. We get destructive interference. Again, this is interference with looks like a spring or a slinky or some sort of rope or bungee cord, but it happens with all waves, including sound. And with sound, what we get is called beats. And those beats are periods of alternating louder or softer sounds. And those alternating louder and softer sounds sound like this. So we call those louder sounds beats. And the beats occur, specifically the louder sounds occur when two waves, again, this is not one wave. What you heard was not a single sound wave just being made louder or softer. It was two waves being played at the same time. And when that happens, sometimes those waves hit your ears in phase and you get constructive interference. Sometimes those waves hit your ears out of phase and you get destructive interference. It's two sound waves being heard. The sound waves are interfering with each other. And the reason that it alternates is because those sound waves have different frequencies and they're interfering with each other. And it's again created by this constructive and destructive interference, which I talked about a minute ago. Often I talk about this is if you play a musical instrument, this is often heard when you're tuning. And it doesn't really matter what it is, trumpet, trombone, guitar, bass, doesn't matter. If the frequencies that you're playing are just slightly off, you can hear a sound that's sort of like this. You can hear those beats. Sometimes musicians call them waves, quote unquote, but they're really called beats in physics. Here's why we hear those. This is very similar to, you ever been on the road in the car and you're in the turn lane and you're looking at the car in front of you and he has his blinker on and you've got your blinker on? You might notice if that's occurring that there are times when your blinker is exactly in phase with the person in front of you. It's on when his is on and it's off when his is off. But if you keep watching, you might notice that those blinkers get exactly out of phase after a while, where his is on when yours is off and yours is on when his is off, right? So they're out of phase. But then if you keep watching, those things begin to gradually get back in phase with each other again, and they're both going at the same time. You might have seen that before. Well, the reason that happens is because blinker frequencies don't exactly match up. They're not always exactly the same. So sometimes they're exact, but sometimes they're not. Well, the same thing happens with sound. So what happens is this is wave one or wave two, or like that person's blinker in front of you, and this would be your blinker. Sometimes they match up exactly. That would be what we call in phase. Sometimes they match up not exactly opposite. So like yours is on when theirs is off. That would be kind of like out of phase. And those conditions alternate. The in phase alternates with the out of phase. We get an in phase and an out of phase, an in phase and an out of phase. And with a wave, when they're in phase, they constructively interfere. And we get a higher amplitude sound. And remember, amplitude with sound contributes to loudness. That's why we hear the loud sound. When they're out of phase, they destructively interfere, and we get the soft sound, the lower amplitude sound. So that's why you heard in that first demo the beats, the loud, soft, loud, soft. It's the result of alternating constructive and destructive interference. Now, we need to talk about beat frequency. That's just simply the number of beats you hear per second. It's the frequency of beats, right? We could talk about a frequency of anything. Well, there's a beat frequency. It's the number of beats per second. You need to know how to determine the beat frequency, and it's super easy. It's the difference between the two frequencies. In other words, all you got to do is subtract. Subtract the two frequencies. So a couple examples here. That was the sound that you heard earlier. I'm going to play it again. I want you to see if you can measure the beat frequency. Count the number of beats that you hear per second. You could go back and play it again if you want, but I heard about 3 beats per second, right? And the reason I heard that is because I know how this was produced. It was a 440 hertz sound wave being played at the same time as a 443 hertz sound wave. You hear 3 beats per second. The beat frequency is 3 hertz because those frequencies are 3 hertz apart. If we take 443 minus 440, and don't ever put negatives in this, you get 3 beats per second. So the difference between the two frequencies, regardless of negatives, the difference between the two frequencies gives you the beat frequency, tells you how many frequencies, how many beats you hear per second. So here's an example that I want you to think about. You got a trumpet, plays a frequency of 784 hertz. Now another trumpet is nearby. It's also playing a note. It's close to the same frequency, but it's not the same. And you can tell because you hear those waves, you hear the beats. Now, let's say we count those beats and we hear a beat frequency of 5 hertz. We hear 5 beats per second, right? If we hear 5 beats per second, we can figure out the other frequency. What could be the frequency of the other trumpet? What could be the frequency of the note being played by the other trumpet if the first one is at 784 and we hear 5 beats per second? What could it be? Pause the video and figure that out. So hopefully you figured out that if it's difference, you're either going to subtract 5 from 784, which gives you 779, or you could also add 5 to 784. It still gives you a difference of 5, and you get 789. So either we get 784 and 779, or it's 784 and 789. In either case, if either of those is the note being played by the other trumpet, we get a difference of 5 hertz, and we hear 5 beats per second. So that's interference and beat frequency with sound.